SwayamPrabha. Digital India. Educated India.
In this lecture, we'll be discussing how we can write a higher order system into first order OD form, and then how we'll be deriving the equilibrium point from those first order systems. After finding the equilibrium point, we'll find the Jacobian matrices using the Taylor series expansion. And from those Jacobian matrices, we'll find the state space representation of the system. We'll have few more examples on how we can apply this method, then we'll conclude the lecture. So let's continue from the next previous lecture. We had pendulum system, nonlinear pendulum system. That system L d square theta t t square plus g sine theta t equal to 0. And we have equilibrium point zero, 0, and pi 0. This is already have done how we have this equilibrium point. And about this equilibrium point, we had two Jacobian matrix. The equilibrium point at 0, 0, we had matrix 0, 1 minus g by L and 0. From this is basically a Jacobian matrix at equilibrium point 0, 0. Now, from this matrix, we can come up with some equation which is called characteristic equation. So characteristic equation you can find using this matrix lambda I minus A, the determinant equal to 0. So this is how we can find the characteristic equation. Now, if you substitute the dimension of the matrix is 2 cross 2, so your identity matrix will be 2 into 2. So here we can write lambda 0, 0 lambda, and minus, we have matrix 0, 1, minus g by L and 0. So equal to 0. And from this we can write lambda minus 1 and g by L and lambda equal to 0. And if you solve this equation, we'll have right here lambda square plus g by L equal to 0. And the roots, we can find the roots of this characteristic equation. We can find lambda 1, 2, that's 2 roots, plus minus I, the complex number, over g by L. And solution, the solution of the system, this is the system for this Jacobian matrix. We had the, not solution, the equations of the system. We had something, right? x1 dot equal to x2 and x2 dot equal to g by L minus g by L x1. So this is the expression we had. And so x1 is the variable, basically x1 of t, or I can write theta of t is the only variable we need to find the solution. This is the only output, that this is the only state appears in the output equation. So solution for this system, we can write x1 of t. Also, you can find the solution for x2, but here x1 of t is the only variable we're going to measure as the pendulum rotates around the reference point. So x1 of t or theta of t, we can write the expression c1, or I can write a1, some constant, sine root over g by l t plus a2 cos root over g by l t. So if you notice carefully, the expression we had for the equilibrium point 0, 0, the same expression we are getting here. If you look the second case we are having at equilibrium point pi 0, and the Jacobian matrix at equilibrium point pi 0, we are having a matrix, we are having 0, 1, g by l, and 0. And the corresponding characteristic equation, of the above system, we can write lambda I minus A equal to 0. If you substitute the matrix lambda 0, 0, lambda minus 0, 1, g by l, 0 equal to 0. And from this, we can write lambda minus 1 and g by l and lambda equal to 0. This is also minus here in this case. And the equation is obtained to be lambda square minus c by l equal to 0. And from this, we are having two roots, lambda 1 and 2 roots. We can write plus minus root over c by l. And the solution we are having x of t or theta of t, we can write c1, we can write c1 into the power plus c by lt plus c2 e to the power e exponential minus root over g by l t. So here also the same expression what you had before, the same expression we are obtaining here for theta of t. So what is the takeaway from this concept? So there is two ways we can come up with the linear system from the nonlinear model of the dynamical system. So here also, if you see the response for the respective system, so this is my t-axis and this is the theta t-axis. And for the equilibrium point 0, 0, we are having the response. Let me write. This is the case for the 0, 0 equilibrium point, and I can write this is the equation number 2, and let's write this is equation number 1. So here, this is the response of equation 1. And for the, basically the equilibrium point for this case is 0, 0. And if you look the response for the equation number 2, we are having some kind of response. It is basically diverging. So this is basically the response for equation 2. And equilibrium point basically in this case 0, 0, the equilibrium point. So now this is basically the behavior of the system, natural response of the system. There is no perturbation, no control, and this is basically how the system behaves with time, natural system. Now the control, what is the role of control here? So control basically, let me write, what is the role of control here? So let me explain it. Now let's assume we have a controller. This is our controller here, and who is giving the desired input to the pendulum system. So we can modify the equation d squared theta dt squared plus g by l sine theta equal to u of t. Some control we are applying to the system. And due to the perturbations to the system, let's assume we have having some perturbation or disturbance to the system. So we are having some disturbance to the system. So let's assume we are having some disturbance d of t to the system. So due to which the pendulum shifted to some another position here. Let me use different color here. But with using this control, we can make the pendulum back to the equilibrium point, and we can take it there always in the future time. So that's why control is very important. Even the system deviates from the equilibrium point, with the help of this control algorithm, we can take it back to this point again. And we can also look because this is already in stable equilibrium point, but the response what you have here, it is basically oscillatory, right? So also we can using the control, we can damp out those oscillations. Suppose the response for stable equilibrium point, we are having the response something like this for the natural system. But with the control, we can modify this response something like this. As time proceeds, it goes to the equilibrium point. Initially, maybe there is oscillation, but we using this control law, suitable with the design of the suitable control algorithm, we can modify the response of the system. So that's why control plays a dominant role for any dynamical system. Even in the case of aircraft, suppose this is the point we are having aircraft, and due to the disturbance, it's shifted to some other point, and using the control algorithm, we can take it back to the equilibrium point again. And also, even if it's the stable system, using the control algorithm, we can improve the response. We can fulfill our mission objective using the control. And let's take another example, and how the linearization we can come up with. In the previous example, you'll have another example, then you'll have better picture how the linearization works for the nonlinear systems. Let's take an example. Y double dot equal to minus y plus y cube plus u. So in this system, we have control. Also, we have nonlinear terms, y cube. So this is basically highly nonlinear system. Nonlinear system. Now we have to come up with some linear system from this nonlinear equation. The question is, obtain the state space representation of the above nonlinear system, and B, find equilibrium point for u equal to 0. So we know that to find the equilibrium point, we have to consider the total moment and force are balanced. So you can assume total force or torque acting on the system assumed to be 0. Then only you can find the equilibrium point. So let's start with the solutions. First, we'll change the variables. This is the second order system, so we have to come up with two first order system. Let's define x1 equal to y and x2 equal to y dot. And from this, we can write x1 dot equal to x2 and x2 dot equal to minus x1 plus x1 cube plus u. And this is, we can denote as, let's define, this is f1, x1, x2. Now also you can write x2u because we have some control here, and f2, x1, x2, and u. Then both the equation you can write f1, x1, x2, u, and f2, x1, x2, u. We can write f x u. So here x is the state vector here. State vector. Okay. And the output equation we can write, the output equation we can write y equal to x1 because y is the only variable we are measuring here. So we can write the output equation y equal to x1, which is nothing but g x u. We can denote as we have mentioned the notations during the linearization technique, the same way you are moving. Now we'll find the equilibrium point for the system. So to find equilibrium point, we have to assume at equilibrium point, we need to assume f x u equal to 0 because this function will satisfy at equilibrium point. So from this, we have to, and also we have to assume u equal to 0 in the equation. So let's write x2 is the function, first function, second function, x1 plus x1 cube plus u. This is basically our f function, this function. So now, if you substitute equal to 0, we'll have, we need to, as we have, this equation should satisfy 0, 0. This is the condition. And from this, we can write x2 minus x1 plus x1 cube equal to 0, 0. From this, we can write x2 equal to 0 and x1 equal to 0, minus 1 and plus 1. So from these points, we are having three equilibrium points. Therefore, we have three equilibrium points which are x, e, I can denote. First equilibrium point is 0, 0. And second equilibrium point 1, 0. And third equilibrium point is minus 1 and 0. So it is quite obvious that we are going to have three different linear systems from these nonlinear equations. at the different equilibrium point, we have defined linear model of this linear system. So first, linearize the system. First, linearize the system at, let me assume x bar equal to 1, 0. This is the first equilibrium point. Let's move with this equilibrium point first. So we have Jacobian matrix dou f dou x, we can write dou f1 dou x1 dou f2, sorry, dou f1 also this, dou f1 dou x2 dou f2 dou x1 and dou f2 dou x2. And if you substitute in this expression, we can, if you substitute f1 equal to x2 and f2 equal to minus x1 plus x1 cube plus u, if you substitute in this expression, we have 0, 1, minus 1 plus 3x2 square and 0. And at the equilibrium point, so let me write, this is my A matrix. This is the state matrix. And E at equilibrium point 0, 1, 0, sorry, 1, 0, 0, 1, minus 1 plus 3x2 square, 0. At 1, 0 equilibrium point, this matrix yields to be 0, 1, 2, 0. So this is our state matrix. Now we'll find, if you go back to our linearization technique, we have to find A, B, C, and D matrix. Now A matrix we have found. Now we'll find the B matrix, dou F and dou U. So we are having there only two function and one control. So we can form the matrix dou F, dou F1, dou U, and dou F2, dou U. So we have values, dou F1 with respect to U is 0, and the second value yields to be 1. If you see the output equation we are having, this is the only output equation x1. So we can write, we can form the dou, we can find dou z, dou x1, and dou z, dou x2. So this yields to be 1, 0. Because z is function of x1 only, so this is my C matrix. And D matrix we can form dou z and dou u. So there is only z is the only function, and with respect to u it will be 0. So we can now form the linear system because we have found all the matrices: A matrix, B matrix, C matrix, and D matrix. So state space form, the state space representation we can find, if you write in error form, the way you have done before, if you write sigma equal to, for example, x minus x bar, and phi equal to u minus u bar, and w equal to y minus c x bar u bar, will have sigma dot equal to A sigma plus BV and W equal to C sigma plus dou dV. So if you write, if you substitute the expression, okay, instead of sigma also we can write in terms of x only, you can write, but to connect with the linearization technique what you have done, so this is how we have represented. So now if you substitute the expression A, B, C, D in this linear system, we'll have sigma dot equal to, if you substitute a matrix 0, 1 to 0, 0, 1 to 0, and sigma 1, sigma 2. This also we can write like in this form, sigma 1 dot, sigma 2 dot, we can write in this expression also, plus B matrix yields to be 0, 1, 0, 1 into B. And we can write, so here only one control, so V's dimension is 1, and W expression will be C is 1, 0 into sigma 1, sigma 2, and this is the D is our 0. So D is 0 basically. And from this, we can come up with the linear model sigma 1 dot equal to sigma 2 and sigma 2 dot equal to sigma 1 plus V. This is our state equation, and the output equation we can write W equal to sigma 1. This is our output equation. So this linear model we found for the equilibrium point, for the equilibrium 1, 0 equilibrium point. So let's look the 0, 0 equilibrium point, how the equation we can find for 0, 0 equilibrium point. The similar step can be followed. We have the state matrix. The state matrix is A is 0, 1, minus 1, 3x squared, and 0. Thus, state space representation at equilibrium point 0, 0, for example. In this case, our A matrix supposed to be is 0, 1, minus 1, plus 3x2 squared, 0. And at 0, 0, the matrix yields to be 0, 1, minus 1, and 0. And B matrix, so B matrix will remain to be same. It will be 0, 1, we can calculate. And C matrix will be again 1, 0. And D matrix will be 0. And the state space representation of the nonlinear system, the nonlinear system at equilibrium point 0, 0, we have sigma dot equal to A sigma plus, we have done, BV, and W equal to C sigma plus dV. Now, if you substitute all the expression, we'll have the state equation. This is basically state space representation. State space representation in linear form. So now the state equations, we can write sigma 1 dot equal to, we can write sigma 2 and sigma 2 dot equal to, we can write plus d. This is my state equation. And the output equation, we can write W equal to, it will be only sigma 1. So this is the output equation. Also, we can find the same way that a linear model of the nonlinear system at equilibrium point -1 and 0. So this is the homework for you. So this is how we define the linear model of a nonlinear system through the concept of linearization. And let's stop it here. We'll continue from the next lecture. We'll be coming with some new topic. Thank you.